Let's continue our discussion about chemical kinetics, which is the study of reaction rates. So far we looked at balanced chemical equations and we were able to set up a relative rate with respect to any reagent or product based on the balanced reaction. Now next we're going to look into what's called the reaction order and the integrated rate law. And before I elaborate on the details, I want you to take a look at this chart here. Track it down, open it up on a different tab, print it out, have access to it while we are going through this discussion and while you're working on problems, because this will be provided to you. It has all of the equations we will be using. I already mentioned rate law and integrated rate law, and then we'll also look at half-life. But forget that for now. I'll come back to it when we need it. Just track it down, have it ready so you can look at it, print the slide. Alright, so the two things we're looking at next are reaction orders and the integrated rate law. So now the reaction order is the dependence of the rate on a particular reagent. And so it's not actually based on the coefficient. It's based on the nature of the reaction and the reaction mechanism. So it's entirely possible that even so you have a high concentration of a reagent, let's say you have a reaction as shown here, we have A plus B going to products, and regardless of the fact what these coefficients here are, A and B, it's actually possible that no matter what the concentration of A is, it has zero effects on the rate. Okay, and so that would be called a zero order, and then it can have first order or second order, and so that is simply going to be expressed here by those superscripts next to the concentration of these reagents. So to the m power to the n power. For example, if there's no, like I mentioned, if there's no effect of the concentration on the rate, then m here for A becomes 0, and so m is no longer part of the reaction rate, has no effect on the reaction rate. So that's what that is. And then the integrated rate law, and so you see this word here, calculus. Don't worry, you won't have to do any of this calculus, but we would like to have a dependence of time versus the concentration of a particular reagent that is linear, so that we can set up a relationship or an equation where we can determine the concentration of that reagent at any time during a reaction, and also determine the equilibrium constant here, K. So that's what those two things are. Let's start out with a pretty easy problem here. So 14.37 from the Tro book. This plot shows the rate of the reaction versus concentration of the reactant A for the reaction A going to products. Okay, so on the left here we have concentration on the x-axis and rate on the left. And so what they want to know is what is the order of the reaction with respect to A. And so that one's actually pretty easy, right? So if it's first order, that means if you double the concentration, your rate doubles, and keeping all of the other reagents or reactants constant. And so if you look at any of these points here, the fact that this is linear, has a linear increase, means it's first order. So that is easy to spot right there. But if you go in and look at more detail, you say, okay, so if you have a 0.2 concentration, you have a 0.00 molal per second. If you double that, you go to 0.4, you are also doubling the rate. So that means it's first order. Now, if this was zero order, meaning the concentration has no effect on the rate, it would look linear still, but flat, right? So if you have the concentration of A versus the rate, and this is for zero order, then it would actually look like this. It wouldn't be curved like my goofy writing here, but it would just be a flat, straight line across. And so this is how you can tell that it's zero order. And then if this was second order, which means if you double the concentration of your reactant, you are quadrupling the rate. So that would be an exponential increase. So that would look like this. Okay, I'm running out of space here, but that would be for second order. Okay. And I'll come back to that in a second and look at that some more. But now they want to know, so we figured out the order. It's first order. Now they want you to make a rough sketch of A versus time. So now we have time here and the concentration of A. So you start out with the high concentration at time 0. Let's say this is 0 to 400 seconds. There's no way for us to know the time, so you can pick anything arbitrarily here. What we do know is, based on this chart here, is that we start out with the concentration of 1 mole and we end up with the concentration of 0. So from 0 to 1. And so the rate at the high concentration is going to be higher than the rate at the low concentration. So what that means is you're going to have an exponential decay. So it's going to look like that, and it's also going to look like that for second order, and for first order it's just going to be linear, but you're also going to have a decrease. So that would be B. And then C says write the rate law for the reaction, including an estimate for K. So all of this is always the rate is going to be equal to some sort of constant K times the concentration of all the reactants, in this case it's just A, to the power of the reaction, or the reactant order. In this case it's 1, we don't write that 1. And then if you wanted to include an estimate for K, you can actually take any of these points from the graph. So if you wanted to take, we can take, let's take this point here, right? So we'll take this point here, which has a molarity of 0.6 m and a rate of 0.006 mole per second, and then all you have to do is you solve for K. So K is going to be equal to the rate, which is 0.006 mole per second, divided by the concentration, which is 0.6 m. So note that m cancels, and constant units are going to be per second. In fact, if K has units per second, that always means it's first order. So the order of the reaction is then going to be 1 times 10 to the minus 1. So that's K per second. That would be K. I have it cleaner on the next page. Now for a 0 order, the rate, if you solve for K, that would just be equal to the rate, right? And then for a second order, you have to do rate equals K times concentration of A squared. All right, so second page just shows everything that I already did. It has solutions clean. It's using a different point to solve for K, but it doesn't matter what it is. All right, let's work one more and then take a pause. So this reaction is first order with respect to N2O5. So we just have one reactant. So the rate law is always going to be rate times, I keep forgetting the K, times concentration to A to some sort of integer. And so if it's first order, it's 1. And so once you do calculate the rate of the reaction, when the concentration of N2O5 dinitrogen pentoxide is 0.055, they also give you a K. So that's pretty easy. So you just plug in the rate equals 0.053 per second times the concentration of 0.055 m, and so that gives me 2.9 times 10 to the minus 3 units mole per second. So m per second, which is what we want. It's a rate. It's something that's consumed per per second or over time. So molarity per second is our rate. So that would be the rate of at that concentration. So that part's pretty easy. So now they want to know what is the rate of the reaction at the concentration indicated in part A if the reaction is second order, and then they want to do this for zero order. Assume the same numerical value for the rate constant. Okay, so the one thing that does change here are the units for the rate constant. Because for zero order, if the rate is simply equal to K, and if K was per second, then your rate would just be per second, and that we don't know. That isn't possible. We know our rate's always going to have to be this. This is a rate, molal per second. So that means that our constants unit are changing. So the constants units are going to be 0.053 molal per second. So that's important. And so this is for zero order. And then for second order, the rate is going to be equal to K times the concentration. So we're going to keep the concentration the same, 0.055 m, but now to the second power. And so if I take m, just looking at the units, if I take m to the second power, that's m squared. And if my rate is in molal per second, the units of K have to be in per second and molal. So let's adjust those units. So 0.053 molal per second. So that when you square 0.055 m, one of the molar capital M's cancels, and our rate is going to be in molal per second. And so I don't remember what that is, so I have to look this up. And this is equal to 1.6 times 10 to the minus 4 molal per second. Alright, so this is just, again, a summary here. Zero order, it's equal to K, and again take note that the units of K, depending on the type of order, changes. And so that's also reflected in the chart. Alright, so I'm going to take a break, and if you have still energy, just go watch another lecture.